Hari Om. In this video, we discuss calculation of adiabatic constant of a gas. You know that adiabatic constant is nothing but the ratio of specific heats of the gas, that gamma equal to Cp by Cv we have already defined. Now, how to arrive at that condition and what is the value of gamma? That is what we are going to calculate in this one. So, let us begin with the first one, that is gamma of monatomic gas. Now, to calculate this, we consider a monatomic gas. 1 mole of monatomic gas taken in a constant volume cylinder and heated through a temperature T. So, when I take a constant volume cylinder and 1 mole of gas inside, 1 mole of gas, and I am heating it to a temperature T, that means the energy Q associated with that gas will be equal to M into Cv into T. That is, I can substitute for this as 1 into, that is 1 mole into Cv, that is molar specific heat into the absolute temperature T. So that I can have a value dq by dt, which is equal to Cv. Alright. So, rate of change of energy, one minute, it is dq by dt. dt, the temperature. The heat energy by temperature will be equal to what? Cv, that is the constant volume specific heat of the gas. And this is the molar specific heat I am taking here. Now, I use the equipartition of energy. For a monatomic gas, we got the number of degrees of freedom as 3. You already understood. Therefore, according to equipartition of energy, the energy associated with this gas at this temperature will be equal to 3 times 1 by 2 RT. Means each degree of freedom must have half RT per mole. We have taken 1 mole of the gas. So, half RT into 3, therefore, Q equal to 3 by 2 RT it comes. This is according to equipartition of energy, that you must note down, according to equipartition of energy. Then we substitute. Now this is, from this you get dq by dt will be equal to 3 by 2 R. Now comparing equation 1 and 2, we get Cv equal to 3 by 2 R. One important relation. For monatomic gas, Cv is equal to 3 by 2 R. Now therefore, Cp minus Cv equal to R, Mayer's relation we have for the molar specific heats, and therefore Cp equal to Cv plus R, and therefore we get Cp is equal to 3 by 2 R plus R, that is equal to 5 by 2 R. That means Cp is equal to 5 by 2 R. So monatomic gas, Cv is equal to 3 by 2 R and Cp is equal to 5 by 2 R, and therefore the adiabatic constant gamma is equal to Cp by Cv, that is equal to 5 by 3. So gamma equal to 5 by 3 for monatomic gas. So the steps very simple. You are starting with 1 mole of a monatomic gas taken in a constant volume cylinder and heated to an absolute temperature T. Equation. And then substitute for the same thing according to the equipartition of energy, 3 degrees of freedom, and therefore you got Cv. From Cv and from Meyer's relation you can get Cp and then find Cp by Cv. This is the case with gamma for monatomic gas. It is 5 by 3. Then if I substitute, if I take the case for diatomic gas, if I start with diatomic gas, gamma for diatomic gas, then what are changes are coming there? By now you might have understood the variation there, that if I take diatomic gas, the number of degrees of freedom will be changing. Now in the beginning again you take 1 mole of diatomic gas is taken in a constant volume cylinder and heated to an absolute temperature T. So that Q equal to M into Cv into T. Therefore, you can have the first part of the statement like this itself. Now, second one, for diatomic gas, the number of degrees of freedom is 5. Number of degrees of freedom is 5, and therefore, according to equipartition of energy, the energy associated with the gas must be 5 times half RT, and therefore Q equal to 5 by 2 RT, and therefore dq by dt equal to 5 by 2 R. Equation 2. Comparing equation 1 and 2, we get Cv equal to 5 by 2 R. Another important equation. Now you take Cp minus Cv equal to R. Meyer's relation. Therefore Cp equal to Cv plus R, and therefore Cp equal to 5 by 2 R plus R will be equal to 7 by 2 R. So Cv equal to 5 by 2 R, Cp equal to 7 by 2 R for diatomic gas. Therefore Cp by Cv equal to, dividing these two, you get 7 by 5. Okay? This is how you are deriving it for diatomic gas. Now like this, you continue with the triatomic linear and triatomic non-linear. Triatomic linear and triatomic non-linear, if you start with the same way, you get the values as triatomic linear. Triatomic linear gas. So, gamma for monatomic gas, we got it as monatomic gas 5 by 3, and second one we got gamma for diatomic gas, that is 7 by 5. Then the third one, gamma for triatomic linear gas, it is 9 by 7, because for triatomic linear gas, number of degrees of freedom is 7, and therefore Cv you are getting 7 by 2r, and Cp you are getting 9 by 2r. Therefore, gamma will be equal to 9 by 7, because 7 is the number of degrees of freedom. And then comes the fourth one, that is gamma for triatomic non-linear gas. You can have it as 8 by 6, because for that C number of degrees of freedom is 6, and therefore Cv equal to 6 by 2r and Cp equal to 8 by 2r, and therefore it comes as 8 by 6. You can shorten it 4 by 3, but don't do that. Now if you analyze all these equations, you can find that the denominator of all these is representing the number of degrees of freedom for that particular gas molecule. Okay? So 3 degrees of freedom means translatory motion only. Then 5 degrees of freedom means 3 translatory plus 2 rotational. And then triatomic linear gas, 7 degrees of freedom means what you call the 3 translatory, 2 rotational, and 3. Sorry, the third part is the remaining 2 is for vibrational motion. And here also translatory plus rotational plus vibrational will be given. Understood? So if I give you a gas with n degrees of freedom, if I give you a gas with n degrees of freedom, then gamma will be equal to n plus 2 by n. From this result, you can directly write the result for n degrees of freedom, that all the numerator is coming as what? Plus 2 of the denominator. 3 plus 2, 5, 5 plus 2, 7, 7 plus 2, 9, 6 plus 2, 8. So, n, then n plus 2.